Hello everyone. In this video, we are going to discuss regression for the classification or the logistic regression, and video level is going to be for the beginner. So thing we are going to discuss today is why we want to use regression for classification, how we are going to do that, what is the mathematics behind it, and the algorithm. We will create the algorithm using NumPy. And also the all of the graph in this video is generated by Desmos graphing calculator. All right. So we have this linear regression equation, right? Y is equal to mx plus c, or we can say y is equal to beta x. And what we want, let's talk about in the binary right now. Okay, we want to have it as a classification that it should output either this particular thing belongs to the class 0 or it belongs to the class 1, or we can say it is either cat or a dog. This email is a spam or not a spam, right? That's what we want. Okay, and why do we want to do that, right? So the first thing, because we want to do that, and the second thing is that when we have regression models already, why can we not try to make so it can classify? The calculation is very easy, everything is established, we just need to update something, right? So in that sense, let's talk about our classification using regression. Okay, so first thing, what we want to have output between 0 and 1. So our multiplication of beta and x should output 0 and 1. Is there any problem? Yes. The problem is that we are constraining our beta and x so that it can give output as a 0 or 1, right? And do you understand? We cannot create the complex model by this way. Let's say we are classifying the images even with the resolution of 10 by 10. That means we have 100x or 100 features. So how can you adjust the beta when your x have 100 features so it can output 0 or 1? That means you are going to drop too many amount of features, right? So we can never be able to create the complex model if we just straight up use linear or polynomial regression and say that, bro, you need to output 0 or you need to output 1. So we need to think in the probability sense, right? So let's take a probability as a measure. Can we use it? Yes, we can use it. So what we want our model to give us a probability rather than saying 0 or 1. We want to say that this particular thing or this particular x belong to this particular class with this probability, or let's say the this input image is 80% belongs to the class 1, or 80% belong, or 20% belong to the class 0, right? So how can we do that? How we can say that this b and x is going to be probability, right? Because probability is between 0 and 1 or 0 to 100 percentage. So probability is going to be 0 and 1. So what we are trying to look here is we want to squeeze the output between 0 and 1, and then we can say it's a probability, right? So let's take a log p. Can we use the log? No, we cannot use the log. The reason being is that if we try to find the p value here, right? If you send the log there, so it is either e raised to beta x, or if here is e, or 10 raised to beta x. On whatever the case is, that your output is already above greater than 1, right? Let's say in the case of e raised to beta x, e is 2.7, and let's say your beta and x multiplication got 1. All right, you have answer 1. So 2.7 raised to 1 is 2.7, which is greater than 1. So it is not giving us anything. So it is not giving us any value which is between 0 and 1. All right, yeah. So what about log odds, right? It makes more sense that rather than just saying what is the log for this particular thing to belong to the class 0, or we can say that what are the odds for this particular x to belong in the cat group or belong in the dog group, right? That makes more sense. Okay, so let's try to find the value of p. Okay, so how we can do that? So we have log e, p divided by 1 minus p is equal to beta x, right? Of course, we have defined it here. All right. So now let's send a log e there. So it becomes e raised to beta x. We find for p, so 1 minus p goes there. We multiply it, then we separate the p, then we just make equation for p. P is equal to e raised to beta x divided by 1 plus e raised to beta x. Now we can further simplify it. So by further simplifying, what we got, p is equal to 1 divided by 1 plus e raised to minus beta x. Okay, so does our p has output between 0 and 1? So we plot it, and yes, our model has output between 0 and 1. and this is what we call a sigmoid function. All right, you can see this x is your e raised to beta x, sorry, this x is your beta x, and this y is the output of our sigmoid function, which is the squeezing function, right? 0 to 1. And you can see the value is always between, y value is always between 0 or 1. All right, now you may be thinking, if you don't understand about the log odds, why we took log odds, if you don't understand, then just think, okay, I will take you from the different perspective. Okay, what we want to squeeze our model output into 0 and 1 after it outputs, all right, not before. What I mean, we don't want to say our model to say 0 or 1, but we want to say, we want to give a freedom to our model that it can say whatever it wants, from positive infinity to the negative infinity, whatever it want to say. But after we will squeeze it, or after we will squeeze it between 0 and 1, so it is probability, right? If you squeeze it between 0 and 1, it is probability. So how do we do that? Okay, so let's say you don't know about log odds and you are not doing anything. You could have figured out this equation on your own. How? So first thing, we need to have, in our equation, we must have beta x because that's what we are squeezing. We must have 0 and 1 because that's what we want, but we cannot put 0 anywhere. So 1 is going to be there. Now you may be doing 1 multiplied by question mark, 1 divided by question mark. Let's say 1 multiplied by beta x, no, output is already greater than 1. 1 divided by beta x, yes, it makes sense. In the case, all right, in the case, let's say your beta x output is greater than 0, let's say it's 100. So your output is going to be 0.01. So it is between 0 and 1. All right. But the problem comes when your beta x goes way below 0. Let's say your beta x becomes 0.1. In that case, 1 divided by 0.1, your output becomes 10. So it is not squeezing every value. Okay. What we can do, let's say 1 divided by 1 plus beta x. All right. In that case, it works. But when the output is negative, it does not work. Or when output is very large, we get precision error. So what can we do? You may try, let's say 1 divided by 1 plus 0.5 raised to minus 0.5 raised to beta x. You may have typed pi raised to beta x, or at the end you may have end up with the e raised to minus beta x. And whatever the case is, here you can put 2 raised to minus beta x, all right? And the results is going to be between 0 and 1, because that's what exactly going to happen if you are going to divide by 1 plus something, right? You could have used pi and the result would have been same between 0 and 1. You could have used 10 and the result would have been between 0 and 1. So why this specifically e, right? So in the logical explanation, because we took log odds, but in our sense, why this specific e, right? Why cannot we use 2? Because when we can use 2 and have the same output. So the reason being is that we are not going to find the value of beta manually, right? Okay, so we will need to take a derivative, right? The good thing about using e is that the derivative of e is itself e, and this is the very nice property to have, right? So that is not the exact reason why we end up with this equation. I mean, if you look at that perspective, then yes, but the more general way was that they started with the log odds and they end up with this equation, right? And it is squeezing between 0 and 1. Okay, so now let's understand what will happen. Let's just summarize. All right, we had our value of x is, right, whatever x we have, and their corresponding beta. We'll let our model output whatever it wants to output. Okay, it may be between 0, or it may be 100, negative 2000, negative 100, whatever our model is multiplying and whatever our beta value is, we allow it to output whatever it want to output. Then we squeezed it using sigmoid function between 0 and 1. Are you able to understand this? All right, think this x as here rotated. All right, this y-x has here rotated. And how we got this equation? When we said that this value or this output is log odds. Are you able to understand this, how we got this sigmoid function here? Okay, now we did it. All right, we have our p-value, we have squeezed everything. So now how do we know that our prediction is right or wrong, right? We need to know if our prediction is right or wrong. So we need to create some sort of function. So what about MSE, right? Y minus sigmoid beta x. Sorry, there is typo. There is going to be the square here, but in regardless of case, Can we use our mean squared error here, or maybe mean absolute error here? Well, you can, but there is a problem. What is the problem? The problem is, let's talk about in extreme cases, all right? When your actual class is 1 and you predicted 0, okay, so that means you made the highest level of error, right? So and look at the penalty. We are going to have penalty of 1. 1 minus 0 whole square is 1. And if the y0 prediction was 1, so this. So we are going to have maximum penalty of 1. That makes no sense, right? You have one error. So how gradient is going to find at all? And if gradient wants to find it, then your computer must have very high precision after decimal points. Then you can use the MSE. And the other problem we have with the MSE is that we do not have prior probability. Rather, we have our y is simple class, right? It is cat or dog. What is our y? Is going to be, it is cat, cat, cat. It is dog, dog, dog. Cat, dog, cat, dog. That is going to be that. It's a class. And what our sigmoid is predicting is the probability, right? So units are different. So in order to use MSE, we must have this, like our y should have been that this particular cat image is 80% cat image, right? It is this particular image belongs to this, 70% belongs to this class. We must have probability, but we are not going to have that. And if we had the probability there, right, if we know already that this particular thing belongs to this much, then we never needed to use any kind of optimization. We could have just used sigmoid, and we could have just took the mean and found out the value of beta directly, right? But we cannot do that. And let's say you may say that, okay, we can do like make a 0, if the value is greater than 0.5, our prediction is greater than 0.5, then we will say it's a 1. That way you solve this issue, right? We made our units same. We said our class, but then you end up with the error problem 1, right? So now what we can do? Okay, we cannot use MSE, so there must be something else we need to do. We need to create the model. So the first, our goal is we are trying to find the model that maximizes the probability for observing data in particular class, right? So we can use maximum likelihood estimation, MLE, which is the method to estimate parameter of assumed probability. I will explain this in very simple term. See, the MLE is entirely different concept in statistics, and it has nothing to do particularly with the logistic regression, right? So I'm not going to explain you entire what is MLE in this video, but I will explain you in the very simplest way. I will give you the intuition what we are doing here. All right. So what we want when our class y is 1, right? We want our p, or our output, e raised to e beta x, our output we want to be as close to as 1 possible, right? That's what we want. All right. When our y is class 0, then what we want our p value to be as close to as 0, right? Or we can say in reverse, we want what is the probability that y is not being in class 1, 1 minus p, right? We are trying to make sure that units are same. Okay. And when you combine them, when you take a conditional probability or joint probability, you end up with this equation, p raised to y into 1 minus p raised to 1 minus y. And this is what we call a likelihood. All right. You may be confusing. You may be thinking how we got this particular equation. This is the lecture, or this is the portion for the another video. But right now I will explain you in the most simplest way what is this likelihood, right? What we are trying to do here. So first thing, likelihood and probability are not same. Okay, probability is just that the probability of something is going to happen, event is happening or event is not happening. That's the probability. And likelihood is that the how likely it is that the given value you are going to find the most amount of your class, or you are going to observe the most amount of data at particular value, or in very simple way, let's say we are talking about the beta. So what is the value of beta at which you are going to find most amount of your observed data, or the value which explains the most amount of your data observed or particular class? That is likelihood. Likelihood and probability is different, and you may be confusing with my words, so I will show you in the different way, but let's just think here. So what we are doing by making this kind of equation, p raised to y and 1 minus y, we actually divided our data set between two groups, right? What I mean is this. Let's say you are doing for class 1, y is equal to 1, then the only part remains is this. right? And this 1 minus 1, it gets removed, so entire part becomes anything raised to 0 is 1. So the only thing remains is this portion. And this for same, if we are doing for class 0, then this portion remains and this portion gets removed. Probability of event happening and probability of it not happening, that's there, right? Yeah. Are you able to understand that? Yes. Okay. So what is maximum likelihood is that we will calculate value of L, which is likelihood, on every change of beta, right? The P sigmoid, where, and we will take the value of beta where L was maximum for overall data set. Let's say we are doing for the class 1. All right, so we end up with this only, this is removed. So our P is 1 divided by 1 plus e raised to minus beta x. Okay, sorry, here is the typo. Here it is beta, not B, by beta x, right? So now what we are going to do is this. We will try random values of beta, right? We will try different values of beta and we will calculate the likelihood. Okay, which is basically this. In case of class 1, it is this, right? And then wherever the and then we will take the value of beta where the likelihood was the highest. What does this mean is that at the value of this beta, or beta is equal to 4, it is most likely that you are going to observe your class 1. All right, that's what it means. Are you able to understand that? Okay, and we are going to do same for the class 0, but we will do it combined, right? We are going to do it combined. Just I separated it just so you can understand. All right. Now this was in the sense of our beta regarded, but now let me explain you in the more sense of statistical way. Okay, let's say you have this, you are trying to classify successful people and unsuccessful people, and based on what? Based on the amount of hours they spend to educate themselves, right? So that is in real life it's not there, right? But I am just making things up here. This is the made up example. All right, and you have this amount of hours they are spending, and you are looking in the successful people. Okay, so what you are trying to do, you are trying to fit the distribution which is most suitable for this data set, right? So what you can do, you try here and you look at the mean of this distribution, how likely it is that you are going to find the most amount of data near to be mean, right? Okay, you found something value. Okay, then you go further, right? And you go further and you continue it throughout the whole value, throughout the whole data set, and you select the distribution mean where you observe the most amount of data. And this is what we call the likelihood. All right, it's probability and likelihood is different, and this is what we call a likelihood. All right, let's go back in our sense. Okay, so how we are going to find the value of beta? Okay, we cannot just try random values of beta, right? We cannot just say 1 to 100 and we will try to find that which value maximizes this function, right? So of course we are going to use the gradient, but what we are going to use, we are going to use gradient ascent. Why? Because we are trying to maximize this function. We want to have maximum likelihood for our beta, right? So we are going to use gradient ascent. But in that sense, we will need to take a partial derivative. So let's just start taking partial derivative. Okay. So we have this p raised to y multiplied by 1 minus p, 1 minus y, right? So let's simplify it and let's take a log. So when we take a log, so what happens? Y log p plus 1 minus y log 1 minus p. And this is also what we call log loss function, all right? And if you are brave enough, then you can just start doing derivation from here, respect to d beta. But we are going to simplify more further, because I don't think it is reasonable or it is logical to do taking derivative from here, because that will be very hard, right? So let's simplify it further. So y log p plus I multiplied inside log 1 minus p minus y log 1 minus p. Okay. Now I join them, y log p minus y log 1 minus p. Okay, that's there. So log p minus log 1 minus p. So that's basically y log p divided by 1 minus p. And what is this? It is log odds, right? So we can just say y beta x plus log 1 minus p. So what is our simplification for likelihood becomes is this, y beta x plus log 1 minus p. Okay, now we are going to take a derivative. This is the reasonable form from which we can take a derivative, right? Respect to d beta. So let's start taking derivative. Okay. we have y beta x plus log 1 minus 1 divided by, okay, that's their p value, p sigmoid function. Okay, so what is going to be derivative for y beta x is going to be yx, right? Okay, now let's go inside. So we have log, right? And what is the derivative rule for log? What you do, whatever is inside, you put it in 1 divided by, right? So here 1 minus 1 divided by 1 plus e raised to minus beta x is there. So what we did, 1 divided by 1 minus 1 plus e raised to minus beta x, right? So log is done. Now we go inside. Now we have this. Okay. Now d beta 1 is basically 0, and then we are going to take it for 0. That's it. All right. And can I say 1 plus e raised to minus beta x as 1 plus e raised to minus beta x raised to minus 1, right? It is 1 divided by that, so we can say that. Okay, so here we have minus left and we are going to take it. But I am here for my easiness, in calculation easiness, I am calling this part as z. 1 minus 1 divided by 1 plus e raised to minus beta x. I am calling it z because it is taking too much space and it is also getting confusing. And when I was taking derivative, I end up making so big of mistake that I multiplied this 0 with something and I end up with the equation 1 minus p. Okay, so that's why we are, for simplification purpose, we are saying it's z. Okay, now let's do it. So here we have 1 minus 1 and we are taking partial derivative. So first function is minus 1, so minus 1 gets ahead, minus minus plus, so we have plus, it becomes negative 2 into d beta 1 plus e raised to beta x. Alright, so now we do it further, 1, so it's 0, and db e raised to minus beta x, and this is where that property of e raised to beta x becomes useful. All right, what is going to be the derivative here? E derivative is going to be e, and with the beta we have minus x, so minus x is going to be ahead. So minus, here we had a plus, now it becomes minus x e raised to minus beta x divided by 1 plus e raised to beta x whole square divided by z. This is there still, right? This is still there. So now yx plus minus minus, right? Minus x, we can simplify it, 1 divided by 1 plus e raised to beta x, right? And into e raised to minus beta x, and it is the same thing, right? We just simplified. I removed x here, so it is easy to understand what I am doing here. All right. So e raised to minus beta x divided by 1 plus e raised to minus beta x is the same as 1 minus 1 plus e raised to beta x. And I was not able to see this pattern by myself. All right, I was end up doing something else, but the answer was the same. But you can see it, let's say multiplied 1 plus e raised to minus beta x, right? If you multiply it with the 1, so we can have similar denominator. Okay, so what you get, 1 plus e raised to minus beta x minus 1 divided by 1 plus e raised to minus beta x. So plus 1 minus 1 removes and you end up with this, e raised to minus beta x divided by 1 plus e raised to minus beta x, right? So we can say that, and we can just remove this z. So what we end up with, yx minus xp, which is xy minus p. So in summary, we have log loss function, which is y log p plus 1 minus y log 1 minus p. Our partial derivative was x y minus p, and if you take in this sense of matrix, then you just say x transposed y minus p. And now, as it is matrix, and this is the most beautiful thing about matrix, is that now you can use this same formula for multi-class classification. Are you able to get it? Because we transpose it, so only thing we need to do, we need to convert into the one hot encoding, and we can use it for multi-class classification. All right, so now let's go for code part. Okay, so here we have this. I am downloading this. It is okay. I have used the cats versus dog dataset of Hugging Face. All right, I don't know how I found out that, but I found it, and this is load dataset, directly will download that particular dataset. And keep that in mind, I am not doing any kind of pre-processing. Okay, we are just using as it is, just to see our algorithm works or not. That is what we are trying to do. We are not making any kind of project here. So I resized all image between 40 by 40. So how many x we have? 1600 1D array of x we have, right? For one image we have 1600 input features. Do you see how complex it gets, right? Just at this small resolution, right, 40 by 40, we have 1600 input values for one image. All right, So how many image we have in trained data set? 300. Okay, 3200 and 800 in validation data sets. That's fine. This is simple uh, normalization dividing by 255. All right. This is evaluate model. That's evaluate function. That's fine. This is our algorithm. Okay. I am using same our previous polynomial regression algorithm. The only thing we need to change is our d beta, right? So here d beta is x norm dot t minus y minus spread, and I have used the minus sign here. The reason being we are trying to maximize the function, right? So either you can use gradient ascent in the sense gradient ascent d beta plus learning rate and remove it. I remove this minus. Okay, I deleted. Or you can say minus here and remove the and keep gradient descent. So both are saying the same thing. All right, you can use however you want. And in the prediction we have sigmoid p, right? Where is it? X dot self beta, and where is the sigmoid function? Okay, 1 plus np e raised to prediction, which is we get. And the only thing I did, I clipped the sigmoid input between minus 15 to 15. All right, so we do not get very high exponential. That's the only thing I did, and other than that the entire model is the same. All right, so we train it for our valid train image and train levels, and we will check for validation dataset. I am intentionally overfitting here just to show you how well our model works, right? How well our logistic regression can classify, just so for that. You can see this is validation. We got 55% accuracy and 52% precision. That's very bad. That's very bad. All right, but we are not doing we are not trying anything. We haven't done pre-processing, nor we are going to do again. All right, but on training set you can see we have 98% accuracy and 97% precision, or 98% precision to be fair, 97.57. So right, so it has learned so much amount of training data. It is overfitting easily. Are you able to get it? What I'm saying? The logistic regression, with the code we made is working. That's what I am trying to say. And I compare it with the sklearn model, and we have similar accuracy. This is training accuracy, which is 92%. So it is not that much overfitted. So in validation accuracy, it has 57, and we had 55. All right, so that is there, and I'm not executing any code just because video is already going to be very long, and the only thing you needed to know about algorithm was already explained in the video, all the maths, and I just showed you how you can implement it here. All right, and this is the experiment 2 where we are going to do for multi-class classification. Okay, so we have this data set of dry bean data set. I found it from online. I don't know from where I found it. I just googled multi-class data set and I found it there. In this data set, we have kind of like bean values. Okay, different types of bean. You can say Y shape is 7. So we have 7 type of beans. It is red bean, green bean. Just think of it as it is, right? And we are trying to classify it. Okay, how many input features we have? 15. Okay, for 1x we have 15 input features, and I train it on just only 1000 epochs, right? And you can see our accuracy here. We got 89% accuracy and 89% precision, or 90% precision. This is on validation dataset. See xval, yval, we got on validation dataset. This is very high accuracy. Are you able to understand? Just on 1000 epochs, right? It is very high. On training, we have similar accuracy and precision. All right. So that explains everything. Okay, so the only thing I wanted to show you was this minus sign, because I am using gradient descent, so I said minus here. And if we are using gradient ascent, that means we add here and we removed minus from there, right? So let's conclude our lecture here. Hey, where is it?